Welcome to today's webinar, sponsored by DigiKey Electronics. Which mesh technology is right for you? My name is Diane Legler, along with Stephen Whitescheid from DigiKey, and we will be moderating today's presentation. To ensure a smooth flow, all participants will be in listen-only mode. Please ask any questions you have throughout the presentation by utilizing the GoToWebinar sidebar on the right of your screen. We'll address all questions at the end of the webinar. Our presenters today are Mark Grierson, Technical Sales Manager, and Matt Dunsmore, RF Product Manager with Digi International. I will now hand the controls over to Mark to get us started.
Good afternoon, everybody. My name is Mark Grierson. I'm Sales Engineer for Digi International, and I'll be talking to you first in this presentation. Just want to make you aware, during this presentation, we will be doing a live demonstration, so want to make you aware of that, so you might stay tuned for that later in the presentation. And also at the conclusion of the presentation, we're going to have a money-saving offer for you. So I think you'll be very impressed with the offer that we have for you at the end of the presentation. And with that, I want to go on and explain, what mesh technology is right for you. Oftentimes when you're using radio products, you see all different kinds of mesh technologies, and Digi is no different. We have two different types of mesh technologies available for you today, and they seem very similar in the way they function. So today we're going to talk about some of the differences and strengths and weaknesses of each one and help you make a better decision on which ones to select for your application. So before we get started on that, though, I want to have a quick review on what is mesh networking. So it's a powerful way to route data. It allows you to extend the range of your application over a great geographic distance, or even in a building where line of sight or point-to-point communications are not possible. Mesh networks are typically self-routing, meaning you don't have to take care of routing tables. You don't have to know the nodes in each hop of the transmission. All you have to do is address your radio, and the routing is taken care of you by the protocol itself. They're also self-healing. If for any reason a route becomes no longer usable, the mesh is capable of rerouting itself to self-heal the network. Currently, Digi offers two versions of mesh modules for you to use. One is ZIGBEE, which is an open standard, and we have also our DIGIMESH proprietary mesh technology. In the near future, we're going to be releasing a thread version of mesh, and we're going to talk about that at the end of the presentation as well to give you a little preview of what's to come. So before we talk about mesh, let's just do a real quick review on point-to-multipoint. In a point-to-multipoint or point-to-point or even a star network, sometimes these are called, every radio has to be in direct RF communication with every other radio in the network. So in this case, radio A can only talk with radio E, D, and B. F, G, and C are out of range and not able to communicate with. So typically in this kind of configuration, we often put a radio module in the middle where D is, and then surrounding radios around it to communicate with, and this is what we call a star topology. The advantage of these point-to-multipoint and point-to-point networks are they're generally faster, have lower latency than a mesh network, but obviously they can't cover as great a distance as a mesh network. They can also be prone to a single point of failure. If our aggregator or base node in the middle of the star goes down, the entire network is basically unusable. Mesh networks, on the other hand, are a little different. Every radio can communicate with every other radio in the network. Routes are automatically determined as we send address packets to each other to different nodes. And if a destination radio is not in immediate range, the message can be forwarded by intermediate nodes. In this example here, I'm showing that radio B wants to communicate with radio N. All we do is address the packet to radio N, and the route is automatically determined through F, H, and K. If we have, the more nodes we add to the network, the more redundant routes we create and actually improve the reliability of the network. If a radio disappears, it's like in this case, radio F, the routes can automatically be rediscovered through a different path. So this obviously a very exciting technology. It allows us to expand our radio applications far beyond what we can reach with a point-to-multipoint network. But there are some drawbacks. One is typically these networks are much slower than point-to-multipoint networks. They have greater latency and greater jitter. So you need to make sure that the application is capable of handling those greater latencies. Now, going over to the two main mesh networks we're going to talk about today. We're going to first talk about ZIGBEE. So ZIGBEE, there are 3 different types of nodes, and each one of these types of nodes has a very unique function and features that they support on the network. There's the coordinators, there's routers, and there's end devices. And there's also ratios that you have to be aware of. End devices require a coordinator or a router to act as a parent node for them, and typically the routers or coordinators can only support about 20 end devices each. So if you're adding many, many end devices to a network, you have to ensure that you have enough routers to support that scalability. So let's talk a little bit more in detail of each type of node and what they do. The coordinator, of which there is exactly one in a ZIGBEE network, is responsible for forming the PAN, or the personal area network. It will select the channel to operate on, and it will also select an operating 16-bit PAN ID randomly. You can also set a 64-bit PAN ID. This can be randomly set, or you can have an administrator set that on your network. But the 16-bit operating PAN ID is always randomly set by the coordinator during startup. Once the network is formed, it allows routers and end devices to join, and it can also act as a trust center when encryption is involved. Routers, they are responsible to join the network. They can act as an endpoint in the network, meaning they can be connected to a device and send data to the coordinator and to each other. They also are responsible for routing data through the network for other routers and end devices. And they also can be used to add devices to the network. So once the coordinator forms and routers join, you don't have to be in range of the coordinator to associate to the network. As long as you're in range of one of the routers, you can join the network through that router. End devices are simply devices that have a sleep mode enabled. So their primary purpose is for battery-powered, low-power devices that you want to, get months, years of battery life out of. So they're responsible to join the network. They support very low power modes, and but they are unable to route data for other nodes in the network. So when I start a ZIGBEE network, here's the procedure. We turn on the coordinator. It selects a channel and a 16-bit PAN ID, and then it starts receiving beacon requests from other routers and end devices that want to join the network. Other routers join the network, their PAN and end devices, and then you can add routers as needed to extend the PAN to the desired size. And these networks can grow quite large. Both DIGIMESH and ZIGBEE networks can grow to hundreds of modules and hundreds of routers. DIGIMESH, on the other hand, only has one type of node. The DIGIMESH node, they're all interchangeable. There's no parent-child relationships to worry about. So the deployment strategy tends to be much simpler. All of the devices can be low-power, battery-powered devices as well. We're going to talk a little bit more about that when we get into the sleeping modes. So starting in a DIGIMESH network is much simpler than a ZIGBEE network, or a little bit simpler. It depends on your point of view. But because there's no association or joining involved, as long as they're configured with the right channel and PAN ID, they're ready to communicate. So very quickly after power up, they're ready to go and ready to transmit. Routers, just like ZIGBEE, can be added to extend the network coverage over great distances. And one unique feature about DIGIMESH is that routing can be disabled selectively on individual nodes as needed. And this is really helpful if you've got a very dense network. You're going to broadcast a lot of data. You may not want to have every node repeating every broadcast, so you can selectively turn off routing to meet your needs. So the way they're addressed, both DIGIMESH and ZIGBEE support 64-bit addresses. These are factory set addresses, kind of like the MAC address of the module. So this is absolutely the best way to address a device because it never changes. ZIGBEE also offers 16-bit addressing, meaning that the radios, when they join the network, they pick up a random 16-bit address. However, this address is volatile. It can change under certain conditions. So when you're addressing ZIGBEE, you almost always still use the 64-bit address. If you don't know the 16-bit address, it will be discovered. If you do know it, you can add it and speed up delivery slightly by doing so. Both modules support broadcast addressing. However, DIGIMESH is much better suited for rapid broadcast addressed packets. The reason for this is ZIGBEE has a broadcast address or a broadcast event table where it can only store 8 events, and these persist for 8 seconds. The purpose of this table is to prevent a infinite loop. But because that table is relatively small, once there are 8 events on the network, no additional broadcast events can be introduced into the network at that time. They'll just be dropped. So relatively slow addressed broadcast ability on ZIGBEE. DIGIMESH does not have this limitation, so it's much better suited for applications such as Modbus, where you might want to broadcast relatively rapid. Some other unique characteristics, or kind of a summary of what we've been talking about here, is ZIGBEE network. I keep saying it's more complex, but it's actually quite easy to get started. But it's definitely more complex than DIGIMESH. DIGIMESH is very easy to get started. You take them out of the box, you plug them in, you feed them serial data, and I'm going to show you this a little later on in the hands-on demo. But they're ready to go. You feed them data and it gets delivered to the other radio. ZIGBEE has multiple node types and ratios to worry about. DIGIMESH is a single node type. So more complex deployment and simpler with DIGIMESH. ZIGBEE is available only on 2.4 gigahertz. It has a maximum range of about 2 miles line of sight with our Pro versions, but it does offer interoperability with other ZIGBEE devices, which can be, a game changer for those types of applications where you need to work with other devices such as home automation devices. DIGIMESH, we have the 2.4 gigahertz for worldwide adoption. We also have 900 megahertz, 868 and 865 for regional deployments. And these frequencies give us better material penetration as well as longer range options, higher output power than is available on the 2.4. But DIGIMESH is a proprietary protocol, only works with other DIGIMESH modules from Digi. Both modules offer similar basic sleep options. So ZIGBEE offers pin and cyclic sleep. Cyclic sleep is where we sleep the module for a predetermined amount of time. It wakes up, sends its data or receives data, and then goes back to sleep. We also offer a pin sleep where you can have a host processor assert a sleep request line to sleep the module and deassert it to wake it up. This is available on both ZIGBEE and DIGIMESH, these basic sleep modes. With ZIGBEE, only the end devices can sleep, whereas on DIGIMESH, we have sleeping router support, and we call this synchronized cyclic sleep. With synchronized cyclic sleep, all the radios in the network can wake and sleep in a synchronized way. This allows for applications where we don't have mains power for our routers. We can put battery power or even a battery with a solar panel, trickle charger, and have very low sleep current devices that are out there. They wake up every 5 minutes, every 10 minutes, every hour, whatever you'd like, and send their data. That synchronized cyclic sleep tends to have a little bit higher current draws because we have to be awake longer to allow all the data to get through the network while it's awake. And the devices have to act as routers for other devices as well. In the basic sleep modes, they both have very low sleep currents, typically less than a couple microamps. As far as the hardware that's available for each one, with ZIGBEE we have 2 form factors available, both a through-hole module for a socketed approach and a surface mount for higher volume manufacturing, or those maybe a vibration, high vibration environments where a soldered down approach is more applicable. So that's available in 2.4 gigahertz only. On the DIGIMESH side, we've got 2.4 gigahertz, 900, 868. We're about to release a brand new 1-watt surface mount XB radio. It's going to be very exciting. It will also support DIGIMESH. And we have a legacy Extend product that also runs DIGIMESH. So many more options on the DIGIMESH side. Just a little bit more information on that synchronized cyclic sleep we talked about. Again, every node in a synchronized cyclic sleep network can route data. All nodes synchronize with each other. There's a sleep coordinator is randomly elected during the sleep process, and then it will send out a sync message at the beginning of each wake cycle to keep all the radios in sync. All or some of the nodes can sleep. Typically, you will have almost all of them sleep, but you may want to have the gateway device in a sleep support mode where it can help bring new modules into synchronization with the sleeping network. And all sleeping nodes share the same sleep timing. And again, this is only available with DIGIMESH. So let's talk a little bit about security. This is an area where that association process of ZIGBEE gives us a couple more options that are not available with DIGIMESH. So with ZIGBEE, we have two encryption keys, two 128-bit keys that are employed. The first one is the link key. This is typically preset at the factory and is shared with all devices. And this is the key that's used to associate to the network. Once we associate, we pick up the network key over the air, encrypted by the link key. And again, the network key is created by the coordinator during startup. It's typically random, but it can also be set by a network administrator. And it's shared with the other nodes, as I said, encrypted by the link key. And the network key is actually the key that's used to encrypt the data that's typically going across the network. Because we have this association process, we can also disable joining on a ZIGBEE network, where we know we've got 6 nodes on our network, they're all joined, we can disable joining, no additional nodes are even capable of associating to the network. DIGIMESH, on the other hand, is a simpler strategy. Again, very secure, 128-bit AES encryption, which is extremely secure on its own, but there is no joining disable, so as long as someone has that key, they can communicate with the network. Both options have support for large networks. Typically, all of our radios have a routing table size that, it depends on the hardware, but for ZIGBEE, it's about 80 nodes, 80 routes that can be stored in the routing table size. DIGIMESH varies on the protocol. The 900 HP is about 135, and the DIGIMESH 2.4 is about 40. But essentially, when you're trying to pull many, many devices in either one of these mesh networks, once you exceed the routing table size, you're going to have to do a route discovery for each pull. And that can be very time consuming and slows the network down tremendously. So we've come up with mechanisms to overcome those limitations on both devices. With ZIGBEE, there's something called source routing and many-to-one routing, where we send out a broadcast that pre-populates a route back to the typically the coordinator from all your remote nodes. And these nodes now, when they send in data to the coordinator, they precede that data with a route record that includes all the hops that are used to reach the coordinator. That route record can then be used to send data back to those remote nodes. So you basically have the address of the remote node and all the hops in between. You feed this packet into the radio, send your transmit packet. They're appended together, and the message is delivered using that source route. Allows you to scale very, very large with ZIGBEE. DIGIMESH, because of the 64-bit addressing, this will be too large to append to the transmission, so we have something called directed broadcast. This allows us to send a special broadcast message with a single address of a remote radio in it. This it goes out just like a normal broadcast, but only the radio with a matching 64-bit address will output that data. So to your application, it still looks like a unicast addressed packet, but it allows us to also scale DIGIMESH very large. In addition to that, we have something called the aggregator support command, the AG command. This is very similar to many-to-one routing command, where we broadcast out a single frame. It will pre-populate a route back to the aggregator and also set the addressing of those remote nodes to the aggregator node. So allows for rapid deployment of large networks. Both modules offer some very unique network diagnostics. Most of these are unique to Digi, but we share many of them on both ZIGBEE, DIGIMESH, and all of our other radios as well. The first 4 are common on both of our mesh network options. The node identifier command is a random freestyle string of text that you can identify a module with. Very useful for when you discover nodes in your network to understand which modules you might be working with. And I'll show you this again in our hands-on demonstration. Network discovery allows you to discover all the radios that are in your network in a rapid fashion, so you can tell if someone's joined to the network. I'm not going to go over each one of these because we are a little short on time today, but all of these are detailed in our product manuals. I do want to address a couple of the ones in the lower section here that have the asterisks by them. These are features that are only available in DIGIMESH. One of them is trace routing. In DIGIMESH, you're able to send a packet with a trace route flag. This will then send back to your transmitting module the route that was used to traverse the network. So really nice for diagnostic and troubleshooting scenarios. Also, the adjacent link test can be very powerful. This is a command that you can initiate locally or on a remote module to test its link with any other neighbor module in the network. You can send up to 1,000 packets of variable size, and what you'll get back is the number of good packets, the number of drop packets, and how many retries had to occur, as well as the strongest RSSI signal strength, the weakest, and the average received signal strength. So very useful for testing links, making sure that you've got a robust network. One more difference between the two is that DIGIMESH is completely silent until you introduce data onto the network. So when you power up DIGIMESH modules, because there's no association and other required network activity, they're just completely silent. On the other hand, ZIGBEE, every router and coordinator every 16 seconds will send a link status message. This is to inform the neighbors of their existence and also populate neighbor tables so they can find out who are their neighbors, who's around, and this information is used for route discoveries. You know, with DIGIMESH, we use a completely different scheme to discover routes. Don't have time to go into it today, but just know that the DIGIMESH network is quiet, the ZIGBEE network is talking, even if you're not introducing data onto the network. So you understand these differences, you get down to decision time, you're not sure which way to go. Here's some kind of a summary of the advantages of each. First and foremost, ZIGBEE is an open standard, and it's another great advantage of ZIGBEE is we've got a fantastic cloud kit, the XB ZIGBEE Cloud Kit, that is a very rapid way to do a proof of concept end-to-end solution with a cloud-based solution. We have our DigiDevice Cloud where you get a free account with that. We've got a development board with sensors built in, and we've got an application that allows you to turn those devices on and off and read the sensors and so forth. This kit currently is only available with ZIGBEE. It's a fantastic way to get started with a end-to-end IoT solution. Everything that we do with that cloud kit is available to be done with DIGIMESH, but the kit currently is not available. ZIGBEE also offers source routing, many-to-one routing, so slightly more powerful in scaling large networks for unicast type applications. DIGIMESH, on the other hand, offers these advantages. Network setup is much simpler. There's multiple frequencies available, more flexibility to expand the network, and I guess this, rather than more flexibility, it's just easier to expand the network. You don't have to worry about end device and ratios and how many routers I've got to support those end devices and so forth. Also, if a router goes down, it's not going to cause end devices to become unavailable because that was acting as the parent for them. So more reliability when routers may come and go. So finally, choose DIGIMESH when broadcast intensive programs such as Modbus, you want to use something like that. Absolutely, Modbus is going to run better over DIGIMESH than ZIGBEE. In fact, it will not be workable with ZIGBEE unless you're using a gateway product with Modbus support built into the gateway. Applications where it's desirable for some nodes not to route, DIGIMESH is the way to go. And also, if you want a very simple scheme, joining scheme, make it very simple for your installers, plug and play connectability, DIGIMESH is going to be a little bit easier. Choose ZIGBEE when you want third-party integration, such as home automation. If you have enhanced security requirements, such as rolling network keys, or you want to disable joining, ZIGBEE is the way to go. And then also when you have end devices that have a parent, you can use something called indirect messaging. This allows you to send messages to those end devices. The parent will queue it up and deliver when the end device wakes up. There are limitations to this. They can't hold them indefinitely. They can only hold those messages for about 30 seconds. So if you're sleeping longer than 30 seconds, it really becomes a moot point. With that, I'm going to turn it over to Matt to talk about some specific examples where each one might be more applicable.
All right. Thank you, Mark. So now that we have a good understanding of ZIGBEE and DIGIMESH networking protocols, I'd like to provide a couple of real-world examples of these different mesh networks in action in the real world. The first example that we have here is in the solar industry. We have a number of large customers in the solar space, specifically in the residential solar, that came to us a few years ago needing wireless capabilities for their solar systems. Devices in these systems included solar panels, inverters and microinverters, as well as in some cases batteries for storage within the home. And each of these assets needed the ability to communicate wirelessly, be easy to install, and connect to a cloud-based application for energy management. Now, in this application, ZIGBEE was really ideal for a couple of different reasons. One reason was that because we have multiple vendors that were involved in the system, in the application, between your inverter manufacturers, your panel manufacturers, and others, having an open standard-based protocol was really important. And ZIGBEE does this. It provides that interoperability between these different devices and gives them the ability to communicate together in a mesh network and play nice. Another reason ZIGBEE was great for this application was because cloud connectivity was required. And a gateway operating as a coordinator on this network, actually inside of the home, connected to their internet connection, provided that function, connected those wireless ZIGBEE networked devices to a cloud-based application and allowed our customers to understand the energy production and consumption data that was being generated by the system, as well as provided them with the capability to upgrade their firmware over the air from the cloud. Next slide, please. So here we have a DIGIMESH example in the oil gas industry, specifically in the upstream oil gas space, oil fields, oil production areas. There are many different types of assets that are deployed across vast areas of different types of terrain. Devices like RTUs, PLCs, all kinds of different sensors like tank monitoring sensors, toxic gas sensors for safety of employees. All of these different types of devices are distributed throughout the oil field site. And every one of these devices requires some sort of connectivity. In many cases, wireless connectivity is great because it's very expensive and often not economical to run wire between the different devices on these sites. And these devices need to be able to communicate wirelessly back to a central control system. And we have a large number of customers who have actually used both our Extend embedded radios as well as our XB Pro 900HP DIGIMESH modules in their devices and actually deployed 900 megahertz DIGIMESH networks onto these sites. Now in this application, DIGIMESH is really ideal for a number of different reasons. One is that since many of these devices are sensors, many of them are actually battery powered or solar powered. And so the ability for every device on the DIGIMESH network to sleep and ultimately reduce power consumption as a result of that is really important. DIGIMESH also enables customers to achieve really good range because they're able to hop between each node, get data from point A to point B, and achieve pretty good range across wide areas of terrain that way. Mark mentioned that with DIGIMESH, network setup is very simple and it's easy to expand your network. So simple network setup and the ability to expand networks for field technicians is a huge benefit in this application. And also, Modbus is actually a pretty common protocol that's used in digital oil field applications. And Mark also mentioned this, DIGIMESH works really well with that particular protocol. So in this case, DIGIMESH is a very good fit for this application. Next slide, please. So in our third example, we'll take a look at the really fast-growing intelligent lighting industry. And a specific application in this industry where DIGIMESH is being deployed today is in intelligent street lighting systems. Municipalities are increasingly looking at intelligent, reliable, and cloud-connected streetlights for their regions because for a number of different reasons. They're safer, they're actually less expensive over time than legacy systems that are deployed today, consume less energy, and because they are wireless and connected, they actually reduce maintenance costs because they're able to provide proactive alerts when there are potential issues with the light. Now, in this case, DIGIMESH is, again, a pretty good fit for this application because it does enable customers to achieve good range with many hops between the network, getting data to every single node, every light on the network. And DIGIMESH supports large networks quite well, scales very well for larger networks of streetlights. And also, again, simple network setup and expansion for field technicians. In this space, as well as digital oil field technicians typically aren't necessarily engineers. They're technology savvy, but the ability to set up networks and provision, commission your devices needs to be very simple and straightforward, and DIGIMESH achieves that. So with that, I'd like to give it back to Mark, and we'll go into our live demo.
All right, thank you, Matt. So as promised, we're going to go ahead and launch our live demo right now. Digi has a free utility called XCTU that allows you to work with all of our radio products. The CTU just stands for Configuration and Test Utility, but this is a really powerful GUI interface that allows you to work with the radios, run range tests, and so forth. As I get started here, I want to kind of just outline the different areas of the tool. On the left-hand side, we have our device area where we add devices to XCTU. And on the right side is where our working area where we see the parameters displayed and basically work with the module that we selected from the left side. And up at the top, we have our menu items to allow us to change between the tools and get help and so forth. So I'm going to go ahead and bring this up full screen so we can maximize our space. There are two ways to add modules. I can click the plus sign and add a module one at a time, or I can use the search button to select different COM ports on my network and add them all at once. So that's what I'm going to do. I know I've got 3 modules connected here locally. So I've selected COM 74, 101, and 102. I hit next. I can now select my baud rate and parity and data bit settings. These are all our default 9608 N and 1. I hit finish. XCTU will then go out and try to communicate with each one of these COM ports and load the radio in. Once it's found all 3, I just hit add selected devices, and those devices are added to my module list on the left side of the tool. I've purposely selected a 900 HP, which I'll use a little later on in the presentation. I have a DIGIMESH 2.4, 2.4 DIGIMESH modules that I want to start the demonstration with. First one is in API mode. I actually want to quickly change this to transparent mode. I can do this by just selecting the parameter down here, the API enable, change this module to transparent mode, click the right button, and the module is changed to AT mode, and this is reflected over on the left. The tool also has a network console mode where I can interface with the modules through a console, a serial console. So if I want to test a quick link between these 2 modules, I can open up this COM port here, detach this from the main view, select the other module, open it, detach it. I now have 2 serial consoles, and whatever I type into one should transmit over to the other. So as I type hello world in one, hello world comes out of the other radio, and I can type back and forth between these 2 radios. So quick way to build frames. I can also use my frame builder down here to create frames and run them with intervals between them and so forth, and basically test the length of my radios. Okay, so going back to this base radio. Oh, I also wanted to point out the name here, base radio. This is that node identifier string I talked about earlier in the presentation. So this can be useful in identifying which radios we're working with. So I'm going to come back to this guy. I can also search for a parameter just by typing its 2-letter designator in the top. It takes me right down to the API mode selector here. I select API again, write that. API mode allows me to do some really unique things on the network. One of them is to use our network working tool, which allows us to map out our network. Not only do I have these 2 modules connected, but I also have about 14 other modules that are running on this DIGIMESH network. If I want to see those, I can click on the scan button here, and those modules will be discovered and displayed in this networking mode view. As it's discovering those modules, you'll notice that lines are appearing between them. Everywhere there is a line between 2 of these modules is indicating a line of, or not a line of sight, but an RF link between those. So everywhere there's a line, these radios can actually talk to each other directly. You'll probably also notice that as this runs, the lines are going to, you know what, this is running a little slow. Let me check my settings, make sure I've got these set appropriately. Let me set this time request slow more rapidly. Okay, this should discover a little bit quicker. So the other thing is, as these are discovered, you'll see colors start to appear. This will indicate strong links versus weak links. And these are all adjustable through our filtering feature. So here are the various categories that we have: very strong, strong, moderate, weak, and unknown. And we have color schemes here. These can all be adjusted through the network appearance settings. So if I want to deem a strong link to be different than 0 to -70, I can do that here and change the color as well. So here we're starting to get some color between our links. A -32, -33 is a very strong link. And I apologize, it's taking a little longer than I was expecting. You can also mouse over each radio and see a list of its neighbors as well as their signal strengths and list. And this all can also be exported using our export option here. I can export the table, and I can also show this in a table mode. So if I come here and select table, it will show me my devices as well as all their connections and associated signal strength. Okay, now another thing that you might discover as you're discovering your network, some nodes will not be in direct range, so you might want to test the link between those. I know on here I've got a radio called Radio X. If I come over to, I'm going to go ahead and stop this and go over to my, oh, I'm sorry, I know what I forgot to show you earlier. Before I went to this mode, I wanted to show you that I can also configure nodes on the network by using the network discovery command. This is the one I talked about earlier, where I can run an ND command or a node discovery command and discover the nodes on my network. I happen to know I've got about 15, so hopefully about 15 will show up here, and I'll be able to add those to my XCTU. Okay, a couple more. All right, there they all are. So I'm going to go ahead and hit Add Selected Devices. These devices, these remote devices, show up as an indented device on my device list, and every one of these I can also read just like they're connected locally. So if I just select one of these and click on it, it's going to read its parameters. It's a little bit slower because it's doing it over the air and possibly over multiple hops, but I can display, change the firmware, reset some defaults, or do whatever I want, just like they're connected locally. Okay, if I want to test the link between any of these two nodes in the network, I can use our range test feature. I come down here in our tools menu, select range test, select my base radio, and over here are my discovered devices. I can select any of those radios. I happen to know Radio X is several hops away from the base radio, so I'm going to select that one. I can configure the payload to be anything I want. Our default here is a Star Wars reference. I suggest a new strategy R2, let the Wookiee win, which is 34 bytes. I can change this to more closely match my application. But once I have that all set up, I can also decide whether I want to loop this test indefinitely or send it 100 times, or there's options there. But let's go ahead and start this and see what we get. As I run this range test, you'll notice that 3 bars appear on this graph at the top. The first one is the percentage of good packets, and right now we're running strong at 100%. The second one is the local signal strength, or RSSI, at the base radio. And the third one is the RSSI, or signal strength, of the remote radio. One thing you'll probably notice here is that these signal strengths are not equivalent. This is an asymmetrical link. And this is because we're going over multiple hops. So these local signal strength is the signal strength between the first 2 modules in the route, and this last one is the last 2 modules in the route. If I stop this range test and select a radio that I know is a neighbor, like I'm pretty sure radio 2 is a neighbor of this radio, I start the range test again, we see that we have a symmetrical link because these 2 nodes are neighbors of each other. So this test or tool is very good at determining whether you've got a robust, reliable network. If I can run a range test with 100 packets, I have no drop packets, and I've got good signal strength, I can be rest assured that I've got a reliable network to work with. One last feature I wanted to show, let me go ahead and remove these radios. Select our 900 HP. this radio happens to use 64 channels. It's a frequency hopper. It only is required to use 25 of those 64 channels. So oftentimes our customers will say, well, how do I know which 25 to use? And in most cases, it doesn't matter. You can use any 25 and they'll work just fine. The default is to use the first 25 of the module. But if you've got noise in the area and you want to determine that, we've got a tool for you built in. We've got a built-in spectrum analyzer. I can select my 900 HP radio here and start the spectrum analyzer. It will now scan each channel, listening for the ambient noise in the area. And when there's noise like we just had there in the center, it will show you the maximum value that was red, the current value is in the blue, we have the minimum value in orange, and the average value in this blue line. So this can be really useful for determining what channel set you might want to use. I can highlight any single channel to see, what its maximum, minimum detected noise was, and I can also look at the graph, looking at the spectrum as a whole. So in this case, I may want to just remove everything and look at the maximum values. So it's easy to see, and I can kind of guess, maybe down here is where I want to set up my mask, or at the top end where there's not quite as much noise. So again, this may save you some money. You don't have to go out and buy a $10,000 spectrum analyzer. You can use the tool built into XCTU. There's many, many more features I'd love to show you, but we don't have time. So I encourage you to download XCTU, start working with it, and just find out how many great features there are to work with.